Alrighty, so this is going on page 111 when we're done. So we have talked about transformations, connected that to symmetry, because you probably didn't even realize transformations and symmetry were connected before. So now today I'm going to take the idea of some of the transformations and symmetry and connect that to functions that you are going to be using moving forward. Now, today we are going to look at graphs that I don't expect you to recognize. I don't expect you to know what the equations are that go with the graphs. I don't expect you to be able to graph the equations that you see. That is all future stuff. What I do want to do is connect it so that you understand that there is a connection. Because I think a lot of times, you know, you leave one math class, you go to the next one, you think it's all brand new and different stuff, when it really does connect to everything that you've been doing. The connections just aren't always there, or if they are, you don't necessarily always see them. So today we're going to look at symmetry and even and odd functions. So why we care whether or not it's an even or odd function and what that means, that all comes later. All right? That's not anything we're concerned with today. We're really just identifying, looking at graphs, that sort of thing. So we're going to look at graphical tests for symmetry with respect to and this should say an axis, not an axes, because that's plural, an axis or the origin. And I'll explain that wording and stuff to you as well here in just a minute. So we've got these three graphs that we're going to start by looking at. And so when I look at this graph, this whole thing right here, this one graph, does this graph, this picture, have symmetry? Yes. Does it have line symmetry or reflectional symmetry? Just reflectional symmetry, right? What is the line of reflection in this first one? Okay, it is y equals 0. Yes, and very good, and thank you for giving me the equation of the line. What else could we call it? Because you're not wrong, that's just not what we call it. It's the x-axis, yes. So the x-axis is the line y equals 0, so very good. But what it has here is it has x-axis symmetry. Okay? X-axis symmetry. So if we reflect this in the x-axis and it coincides with itself, it has x-axis symmetry. You with me? Okay. So this second graph, does it have symmetry? Yes. Is it line or rotational? Line. And what is the line of reflection then? The y-axis. So this has y-axis symmetry. Okay. Then does this graph right here have symmetry? Yes. Does it have line symmetry? No. Does it have rotational symmetry? Yes. What is the angle of rotation? 180. So if I can rotate it through 180 degrees, it also has another special name. What's that? What kind of symmetry I can rotate through 180 degrees? It's rotational, but it's the little subcategory, the only subcategory we're talking. It's point symmetry. So this specifically, not just rotational, but this does have point symmetry. And the point that is the center of rotation is what? The origin. So this is origin symmetry. So it's not just that I can rotate it about the origin, but that I could rotate it 180 degrees. So it's the point symmetry. So when we're looking at these graphs, we only care about three things: x-axis symmetry, y-axis symmetry, or origin symmetry. It is possible that there are graphs that don't have any of those at all. Don't even have any symmetry. Or graphs that have line symmetry, but it's not an axis. Those we're not worried about. These are the only things that we're really truly focusing on to get what we need. You with me so far? All right, so we look at the next part then. So just going to restate some of these things. So we'll start with x-axis. So for the x-axis, a graph has symmetry with respect to, okay, so this is going to seem a little bit repetitive, but it's probably new phrasing that might sound a little weird. Yes, the x-axis is the line of reflection. We would reflect it across the x-axis or in the x-axis is another way to say it. But the symmetry is with respect to something. So it's symmetry with respect to the x-axis. If for every point x, y, so this is asking for the mapping, but without the little arrow notation. Every point, when you have x-axis symmetry, so if this is some random point, and I can reflect it in the x-axis, then this point has a match down here and vice versa. So every point xy has a point, what? What would that look like? X negative y. Good. And you can tell by jotting down a little graph here that your x value stays the same, the y value changes. That is your rule for reflecting in the x-axis, right? And it works for functions as well. That's something that you look at functionally. All right, so then we'll look at y-axis. So a graph has symmetry with respect to the y-axis if for every point x, y. All right, so I've got this point again, but if I can reflect it in the y-axis, it will look like that. So for every point x, y, then there's a point what? Negative x, y, because that would change the sign on y. Easy enough? Then we have origin symmetry. A graph has symmetry with respect to the origin. So that means I'm rotating 180. So if this is the random point I pick, the rotated point that it has to match up with would be down here, right? So every point x, y, negative x, negative y, because that is your rule for rotating 180 degrees, right? Does that all make sense? Okay, so one of the things that we want to look at here, first of all, with the origin symmetry, because there was a little bit of confusion last period. Some people were having a hard time like wrapping their mind around the fact that this had some sort of rotational symmetry. But remember, what's happening is that if I have a point, if this point right here rotates 180 degrees, then when I connect it to the center of rotation, then that right there, that is 180 degree rotation, right? And that works for every single point. So if I picked another one, like here and here, and I don't know how great all my little pictures are going to be here, but if I connect that, I get this line segment there, so then that right there is 180 degrees. And that works for every single point. Okay, so the whole, plus the other way to look at it, I'm going to erase that so you can actually see the graph. The other way to look at it is that if I rotate my paper 180 degrees, pretend like I hit reset on the axes, it would look the same. Does that make sense to you? It coincides with itself. All right. Now, notice the title of this also. The title of this is Symmetry in Even and Odd Functions. Are all three of these graphs functions? No, they are not. And you should already be able to identify, like a champ, whether or not a graph, when you look at it, is a function or not. You should be able to do that by just looking at a graph. You should also be able to do that by looking at a table or, having some other things. So you have to decide, is it that every x has exactly one y, or every y has exactly one x, or how does that work? Okay, you sure about that? Or is it every y has one x? Can you make yourself second guess that pretty easily? And I could ask it in a different way where it would really be backwards and then it would really confuse you, right? Because it's not that it's hard, it's just trying to get that out in the right direction. So you want a way to be able to fill this little sentence in correctly. So for functions, you need to be able to say for every blank, there is exactly one blank. Okay? Yeah, don't write the word blank. So those blanks are x and y or y and x, and you got to make sure that you can wrap your mind around which one they are. One way to do that, whether you need to do it or not, something you still have to be able to do, is to look at a graph and know. So here are two different graphs, right? And one of these is a function, one of them is not. Which one is the function? The one on the right. And how do you know by looking? Yeah, so she's going like this while she's talking to me, right? And so because what is this called? What is this test that she's doing called? The vertical line test. You can call it the vertical line test, or some teachers call it the pencil test, the same thing. If I take my pencil and I run it along the x-axis like this, if my pencil hits the graph at more than one point, then it's not a function. But it's the vertical line test. So like if I drop a vertical line down right here, it hits my graph at 4 points. It can only hit it once to be a function, so that's a big fat no there. This right here, no matter where I put that line, I'm only going to hit it once. Does that make sense to you? Now, so now if you know that much, then you can think, all right, well, this x value, does this x value have more than one y value? Yes. Is that a bad thing for a function? Yes. This x value has only one y value, right? But you see this y value? Does it have two different x values that go with it? Yes. And that's totally okay for a function. My y value can have more than one. So the y value does not have to have exactly one x, but an x value does have to have exactly one y. Does that make sense to you? Those are very important things for you to understand about functions that should already, I mean, it's something that you've already done and already been taught, but you want to make sure that you can wrap your mind around that. Okay, we all good with that? Okay. Well, it is simple. It should be made simple to you. I'm sorry. Okay. Exactly. All right, so now we're going to determine determining even and odd functions from a graph. So whether or not they are functions. So if they're not a function, we don't even care. That's why I only have 2 of the 3 graphs here. Right? It may have symmetry, but it's not going to be a function. So you have a function that is even if and only if its graph has symmetry with respect to the y-axis. Okay? Even functions have symmetry with respect to the y-axis. Why that's the case, why you care, remember, all that's coming later. We're just going to learn what they are and how to identify them so that hopefully it can connect in the future. So then a function is odd if and only if its graph has symmetry with respect to the origin. And if you look back on the front of your notes, then if it has x-axis symmetry, why don't we count that? Because it's not a function, exactly. Okay, we all good with that so far? Okay, so it's not a function, it has symmetry, but it's not even or odd because those are only functions. So when I look here at this graph here has what kind of symmetry? What kind of symmetry? Y-axis symmetry. And since it has y-axis symmetry, it is an even function. Now, I could take that same parabola and translate it to where it ended up like over here. Like maybe, same everything, but just translate it. Does this parabola here have symmetry? Yes. Does it have y-axis symmetry? No. So this is not an even function. These two are very similar to each other as far as properties or whatnot, but this is not an even function and this is because it's all about y-axis symmetry. Does that make sense to you? Okay. So now this one has what kind of symmetry? Point symmetry, which is origin symmetry. It does have point symmetry, but specifically for our graph, it has origin symmetry, which means that this is an odd function. And it does not have to, okay, hang on, apparently I can't spell and talk at the same time there. Okay. It does not have to actually pass through the origin. That was something that some people had gotten confused on, I think, based on the examples probably that I had given, but this happens to pass through the origin. That's fine. It doesn't have to have a point there, but that would still have to be the center of rotation. Y'all cut it out, whatever's happening right there. Everybody good so far? You think you could identify them from pictures? Yes? Okay. So now we're going to look at the equations. Now, I'm not giving you any questions on the equations on the homework. I don't expect you to know what those graphs look like. Nothing. I'm just trying to expose you to this so that you can see that this stuff all does relate to each other. So a polynomial, you should know what a polynomial is, right? Many terms. Okay, a polynomial function is even if and only if the degree of each of its terms is even. So let's talk about that wording a little bit. The terms, what's a term here? Like this right here would be like 5x to the 6th is a term. What is the degree? The exponent. Okay. So the degrees are the exponents. All right. So then a polynomial function is odd if and only if the degree of each of its terms is odd. Now, there are other tests for even and odd that you do so that it doesn't have to be in these forms. We don't care about those right now. But, this isn't the only way to identify them. But it is one that's kind of simple for you to at least see a connection. All right, so when I look here, right, so my first example, I look at the degrees. There's a 6, a 4, and a 2. So is this even, odd, or neither? Even, because each of those is even, so this is an even function. All right, and then here, this is a 3. What is this one? a 1. So what is this, even, odd, or neither? Odd, so this is an odd function. Then here, what is 3 and 2? So what is this? Neither. Good. So then let's look at example 4. This degree is 4. This degree is 2. This is a term. What is the degree? There is a degree, and if I can put the x on there so I can see it. If I put an x here, I can't actually change this, so I can't just leave it x. What would the exponent be so it would still really just be negative what? 0, because anything to the 0 power is what? 1. Negative, no. Anything to the 0 power is 1. X to the 0, a million to the 0 power is 1. Everything to the 0 power is 1. So, looking at those then, is this even, odd, or neither? Even. This is an even function. Yes. Now, he said because 0 is even, right? Yes, but, here's the yes, but. If you went and Googled that, you're going to see all kinds of crazy stuff. So there's lots of discussion on whether or not 0 is actually even. Maybe it's not even or odd. It depends on your definition of even. There's even some argument out there about why it could be odd. That one's a little ridiculous if you ask me. But anyway, it's for our purposes here, and for most purposes, it's an even number. It has those same properties. I know, it's just weird. So, yeah, I know, he was trying to be funny. It didn't work. All right, so what about y equals x cubed plus x plus 2? What do you think about that one? All right, this degree is 3. What's this degree? 1. What is this degree? 0. So is it even, odd, or neither? Neither. Okay. No, that's not the case. Straight number. What's that called? What's the straight number with no variable? Starts with a C. A constant. Good.
So a constant number would be 0.
Yes. The degree is 0. Yes.
So therefore, if there's odd x degrees, and there's a constant.
Yes. Yes. And I'm about to show you why. So that's good. You got it. Got it down. That's okay. That's okay. I know, and your brain was processing it. It's fine. All right. So if I graph well, first of all, y equals x squared. Is that even, odd, or neither? Even. That's easy, right? So when I graph it, it looks something like this, right? Okay. So y equals x squared plus 3. Is that even, odd, or neither? Even, because this is like x to the 0 power, right? Well, when you graph that, what does that plus 3 do? It translates it up. Very good. It translates at positive 3. So sorry, I was leaning in so much. Yeah, my ID's like possessed. Yes, exactly. So, even though that just doesn't even look like I hit the axis there. All right, so this moves it up 3, right? Translates it up 3. Listen, shh. And the correct terminology is translates it 3, like a positive 3, because again, these are translations that you're doing with this. But notice that that's what this constant does, is it's just translating it up or down. And if you look up here, if I had an odd function like this, if I translate this up or down, it still has symmetry, but does it still have origin symmetry? No. And so that's why the constants don't work for this, but will work for this, because it already has y-axis symmetry. And if all you're doing is shifting it up and down, you're not changing that fact. You with me on that? Mm-hmm. Right. Exactly. So just in general, for the even functions, constants, okay. For odd, constants, not okay. And so last period, nobody had tried to use the word constant yet. And so somebody said, what is a constant? So when we talked about that, we finally got that out. Said, well, because this is a variable. Do you know why it's called a variable? Because it varies. The value varies based on what I put it in. This value is constant because it doesn't change. That's why they're called what they're called. Does that make sense to you? Like the words make sense. Yes, exactly. All right. So on this last page, here's what I want you to do at the top of each of these empty boxes. We're going to write that it is symmetric with respect to, kind of, just getting good wording here. And just rewrite that same thing at the top of each box. Symmetric with respect to. Because if you never see the words, you never hear the words, then when they're used with you, they sound all weird and confusing, and you don't even know what they're trying to talk about, and it's really not that bad. It just sounds fancy. Symmetric with respect to okay, so just do that on all three of them, then we're going to go back and talk about them. All right. So let's go back up and look at group A. So here's a group of graphs in A. Do you think these graphs right here are symmetric with respect to what? Y-axis. Do y'all agree with that? Okay. So they are all symmetric with respect to the y-axis. So does that mean they are even, odd, or neither? Even. Even. So these are even functions. Everybody okay with that? Now, the next group, group B, what kind of, these are symmetric with respect to what? The x-axis. Okay, so are they even, odd, or neither? And why is that? Good, because they are not a function. And that's important because they may have symmetry with respect to something else, but the fact that it's not a function is the most important thing. And if you always check that first, you won't even have to check symmetry. If it's not a function, it can't be either one because it's not a function, right? And then the last group has symmetry with respect to origin. And these are what? Odd functions. Odd functions. Good job. Got it out first. Okay. So do you all feel comfortable enough just to identify the graphs? I'm not going to make you identify the equations. I just wanted you to see it and us to talk about it. So now I'm going to hand out your homework, and then we're going to work a few of those together so I can make sure that you understand exactly how I want you to answer these. Okay, so let's look at the front of this. We're going to jump around. We're going to do a few of these together. We're going to start on the front with A. Okay, so A, and the directions here are state whether the graph is even, odd, or neither, and explain. So for A, do you think it would be even, odd, or neither? Okay, so let me ask you this. Does it have symmetry? Yes. Does it have line symmetry or rotational symmetry? Line symmetry. All right. And so here is the line of symmetry. Is that line that is the line of symmetry the y-axis? No. So is it even, odd, or neither? Neither. So the reason is neither. And so in A, we're going to put neither. Now then when you explain it, listen to what you have to do for your explanations. You're not going to say it's neither because it doesn't have y-axis or origin symmetry. That's not your explanation. If it does have symmetry and the answer is neither, then you say what it is symmetric to because it does have symmetry. So it's neither, and it is symmetric with respect to what? X equals 3. Good. Symmetric with respect to x equals 3. Okay, so on Schoology, you're not going to have to type all that stuff in. On Schoology, these are all set up as like multiple choice questions. So you're going to choose even, odd, or neither, and then you choose your explanation, and I'll tell you a little bit more about that after we do the rest of these. All right, so now I want you to look at E. So for E, do you think it is even, odd, or neither? Okay. Is it a function? Yes, okay. Does it have any symmetry at all? No. So if it doesn't have any symmetry at all, it can't be even or odd. So your answer for E, make sure you put it in E, is neither. And it's not symmetric. If you imagine if you were born a graph and you were not symmetric, you would have a terrible life as a graph. All right. So listen. Look at G. What do you think about G? Even, odd, or neither? Neither. And what's your best reason for that? It is not a function. It does have symmetry, and the line of symmetry is y equals 2, but that's not my explanation. My explanation for the reason that G is neither, make sure you put it in G, neither is that it is not a function. If that is the case, that is the best answer and what you have to make sure that you have. Okay? We good? All right. Now look, flip over on the back. We're going to do a couple on the back. So look at D right here. Even, odd, or neither. Okay, so if it's even, then that means I can reflect it in the y-axis, and it looks the same. Can I do that? No. Okay, so, and if it's odd, well, does this have symmetry? Yes. It has rotational symmetry, and that's the point. Is that point the origin? No. So then it does, so then it's a neither situation. So make sure you put it in D. It is neither, and it does have symmetries, and it is a function, so I say that it is symmetric with respect to, and I'm looking for these words, so make sure that you are actually putting them, with respect to what? 0, -3. Why can't I put y equals -3? Because it's not a line. The y value is -3, but if I put that it's symmetric with respect to y equals -3, that's a line, and it's not symmetric with respect to a line. It is has point symmetry, and this is the point that it's symmetric with respect to. It just doesn't have origin symmetry. We all go with that? All right, so the last one I want to look at is H. So do you think that one is even, odd, or neither? Okay, so it has rotational symmetry. It does not have reflectional symmetry, so I know it can't be even. It does have rotational symmetry. What is the center of rotation? The origin. So what is this? Odd. So it has origin symmetry. So H is odd, and your reason is that it is symmetric with respect to the origin. And so every time the answer is odd, the reason is exactly the same. Every time it's even, the reason is exactly the same. If it is neither, the reason changes. And so the reasons that you have in Schoology, I probably won't say them exactly like what they are, but it's something like the reasons will be symmetric with respect to the origin, symmetric with respect to the x-axis or y-axis rather, and then maybe not symmetric and not a function, or symmetric with respect to something other than the y-axis or the origin. That's where this one would go, because I was trying to make it easy for you to answer in there. So in Schoology, you're not going to give me this specific point, but I'm going to look at it on your paper. Does that make sense to you? So it'll just say something else so that it was kind of the same for all of them, but I am looking for the actual, what the other thing is on your paper. Does that make sense to you? So still make sure you write it down. Any questions at all? This is not that bad. It really isn't. It's not like, oh, it seems easy and then it's going to be so hard and confusing. You're fine, okay? And you got about 10 minutes, so you need to make good use of that time. You can get quite a bit of this done.